Hello friends, the ongoing lecture series on topic of advanced manufacturing process. Today I'm going to talk about the abrasive jet machining process. So this will be the lecture 2 of series 1 to 2025, and this lecture video will be published on Nirbhik Sanyogi and Nirbhik Gyan, my both YouTube channels. So outline of this lecture will be, first I will talk about the introduction of AGM, so working principle of abrasive jet machining, as well as the advantage, disadvantage, and potential application of the abrasive jet machining process. I will talk about some on some fundamentals, how mechanics of metal removal of in abrasive jet machining process. So there are several models available, right? So I will talk few of them, and then I will discuss about process parameters which affects the abrasive jet machining process, and then overall summary. And I will also try to solve the worked out some examples. Okay, so first, introduction to abrasive jet machining. So as we know that abrasive jet machining is classified under the mechanical energy source type, as well as the mechanics of metal removal. If I will say, it will be the erosion based, and energy used mechanical and sometimes fluid motions like in water jet machining. It's a another version of abrasive jet machining. We call it water jet machining, right? So as you can see here in this schematic diagram, it involves a high velocity stream of fluid. It may be air or carbon dioxide, any gas, right, mixed with abrasive particles in a chamber, and which is flow through the nozzle. So it will be the high velocity. The function of nozzle is to increase the velocity of mixture, abrasive as well as the gas, right? And it will pass through the nozzle, and it will directly imping on the surface of the workpiece, and the material will get erode in the exposed area. This technique is commonly used for the tasks such as cleaning, etching, cutting, as well as the surface finishing, and mostly on the brittle materials. However, in the past few decades, some of the ductile materials are also being processed through the abrasive jet machining process, and but it is particularly effective for precision work on hard and brittle materials like ceramics, glass, as well as the composites. So you can see the schematic diagram of the abrasive jet machining. So principle. So in abrasive jet machining process, abrasive particles, typically sand, aluminum oxide, silicon carbide, which are accelerated using a high pressure gas, usually air or nitrogen, through the nozzle, and the impact of the high speed abrasive particle as well as the gas mixture causes the material to erode, which leads to material removal. The process is a form of macro machining where the particle impacts on the metal surface at the surface level at high velocity, causing localized deformation. So, and that's why it for this process falls into the non-traditional manufacturing process, because it's a, you can see from the previous diagram here, there's no direct contact between tool as well as the workpiece. So there's a gap, and in that gap, high velocity abrasive with gas mixture flows through, and it directly impacts on the surface. So if you will talk about the abrasive jet machining system, so I will show you the diagram first, then I will discuss. So here you can see there's a gas supply for the gas, and regulator is there, filter. If you, let's say, any particulates or contaminants is there, then it can be filtered out, and it will flow through the go to the reach to the chamber where abrasive jet particle will get mixed with the high gas, and the vibrator is used to to properly mix the gas as well as the abrasive, so there will be homogeneous mixture, right? And that mixture will flow through the tube, and it will reaches to the nozzle. And in the nozzle, the function of nozzle is to increase the velocity of the air plus abrasive mixture, and here it will reaches on onto the surface of the workpiece and the crater which formed that we can see in the cavity form. Right. So here that same thing I have discussed in this slide. Here you can see air compressor supplies high pressure carrier gas, regulator, abrasive particles, abrasive feeder where from the which controlled flow, its function of abrasive feeder is to the stores and deliver a controlled flow rate of abrasive particles to the mixing chamber. Because I will show you, the mixing ratio is a very crucial factor in the machining process. The mixing chamber, nozzle, machining chamber, workpiece holding device, control system, as well as the workpiece. So advantage of abrasive jet machining. So as I told you, it's a non-contact process and the minimal heat affected zone, because the material is removed by the mechanical force, less chance of getting a heat affected zone on the workpiece. High precision, intricate feature. Some of the intricate features can be generated using the AGM process. No residual stress because there's no thermal heat involved, significant heat involved. So that's why there will be no residual stress developed on the workpiece surface. Versatility, and it can be machined wide variety of materials, including hard materials, ceramic, glass, and composites. So AGM machine comes with some disadvantage also, like a limited material removal rate, not suitable for high material removal rate as compared to other machining process like grinding or milling. Precision limitation, since there's a limited control over the flow of the abrasive mixture onto the surface, so there will be some issue with the precision. Not generally recommended for the soft and ductile materials. Dust generation, because it involves the high velocity abrasive mixture, and which creates a lot of dust, so there's a proper filter is required, right? So for the safeguard of the people who is using the machining. Nozzle wear is a significant factor, because although nozzle is a very tough material made of like sapphire, but it is also get wear by multiple uses. And each nozzle material has some life, tool life, we can say. High operational cost, the need of high pressure gas as well as the fine abrasive can increase the operational cost sometimes. Applications, if you will see here, the mostly it's like a glass and ceramic cutting. AGM is commonly used for the drill, cut, and grab the brittle material like glass, ceramic. Surface cleaning, etching and marking, ideal for the etching or engraving on the hard surface. Micro machining, devering, etc. So now I will talk about the mechanics of material removal, how ac- actually material is being removed from the workpiece. So in the AGM process, material removal occurs primarily through the mechanical erosion. Then high-speed stream of abrasive particles carried by gas jet strikes on the workpiece surface at velocity ranging from the 150 to 300 meter per second, and depending on the several factors like workpiece material as well as the feature you want to generate. So several factors are involved to decide on the jet velocity. The mechanism is that so once high speed jet of the abrasive mixture reaches to the surface, it's like a actually kinetic energy of these particles is being transferred upon the impact, causing the localized erosion and material removal. As you can see on this schematic diagram, in the left side you can see the irregular shape of abrasive grain workpiece, and there's a fracture which is created by this abrasive grain, and after the removal of the particle there is a cavity formed on the workpiece. Removals for brittle materials and ductile materials are a little bit different in AGM process. In case of brittle materials, localized impact of the abrasive jet mixture exceeds the fracture toughness of the workpiece material, and which causes the macro crack formation and propagation, and material removal occurs via chipping, brittle fracture erosion we call it sometimes. While in ductile materials, workpiece material, repeated abrasive impact causes the plastic deformation on the surface of the workpiece, which results in a material removal through macro cutting and fatigue, less efficient. And since I told you this is most efficient for the brittle materials, so that's why this is the less efficient than brittle material fracture in AGM process. So here you can see on the schematic diagram here, like in case of brittle material and the ductile material, the fracture profile is a little bit different. So now I will try to estimate the material removal rate of brittle material as well as ductile material both, right? So there are some assumption for that. So abrasive characteristics. So abrasive particles are assumed to be rigid and spherical in shape, although in practical abrasives are not spherical. Each particle is represented by its main grid diameter. We consider it is circular. It is further assumed that entire kinetic energy of the abrasive particles is effectively used for the material removal. It is not wasted somewhere else, right? And in case of brittle materials are assumed to fail primarily through the brittle fracture mechanism. The resulting fracture volume is considered to be hemispherical in shape, as you can see on the left side of the schematic diagram. So the fracture, which is shown by the dash line pink color, and it's like a hemispherical in shape with a diameter equal to the chord length of the indentation caused by the abrasive impact. While for the ductile material, if you will see, the material removal volume is assumed to be equivalent to the volume of indentation, that is the delta, which is created by the impact of the abrasive particles. So these are the assumptions to derive material removal rate for brittle material and ductile material in case of AGM process. So let's assume that one single grain what particles, and it's a, since we assumed it's a, like a spherical, and it makes indentation on the workpiece of with the depth delta, and capital D is the width of the crater which is created by the single abrasive, and small d by 2, it's like a radius of one abrasive particle, right? So if you will do the some trigonometry, and then it will result the radius of the crater you can express using the d by 2 is equal to under square root of small d, means the diameter of the abrasive, multiplied by depth of indentation, that is the delta, right? So the volume of material removal in brittle material, as we assume, that is the volume of the hemispherical impact crater, and it is given by, so we can calculate the volume of the material removal in brittle material. So that will be the 2 by 3 pi d by 2 power q, and if you will put the value of capital D by 2 from equation 1 into this equation, so final expression will be something like this. While the for ductile material, we have assumed like a volume of material removal will be the single impact, which is equal to the volume of indentation only, right? So considering the small value of delta, so I will show you the again the figure, then you can see for ductile material it is the only indentation delta. So here the volume you can calculate using this formula, you can see next equation 3. So now the kinetic energy of a single abrasive particle. So kinetic energy, as we know, that it's like a half of mass multiplied by square of the velocity, and so mass of abrasive you can always calculate using the density of the abrasive as well as the mean diameter of the abrasive grain, so that you can calculate using this relation, and then we can put the mass of kinetic energy expression, then you will get that, where v is the velocity of abrasive particle, ma is the mass of single abrasive grid, d is the abrasive diameter of the grid, delta is the rho is the density of the grid. So now what will happen upon impact? What we assume that the kinetic energy of the all abrasive grains will be directly consumed to remove the material. It will not waste anywhere, right? That is the theoretical assumption. Here, then we can calculate the work material experience a maximum force once it will impact on the surface of the workpiece, which is resulting in the indentation of depth delta on the workpiece. So thus the work done during this indentation you can calculate using equation 5, where it H is the hardness. Now it is assumed that kinetic energy of the abrasive is entirely utilized for material removal. So the what will the work done by these abrasives on the surface, it will be considered equal. So what we will do, we will equate the equation 4 and 5 here. The kinetic energy expression as well as the work done expression will equate it, calculate the depth of crater from the by equating equation 4 and 5. So that will be the equation 6 is the expression for depth of crater. Now material removal rate in AGM for bitter material, as we know, it's like a volume of material removed as in multiplied by number of impacts by abrasive grid per second, right? So how we will calculate number of impacts by abrasive grit? So it's like if we will divide the mass flow rates of abrasives, total abrasive, by mass of single abrasive grit, then we can calculate the small n, which is number of impacts by abrasive grit per second. And this expression we will put in the equation 7. Then also we will take some help from the equation 4. Then the value of n we can calculate, and that value of n we will put in equation 7. The material removal rate for bitter material is finally will come into like this, that equation 11 is a material removal rate for bitter material. So similarly, for ductile material we can also estimate the material removal rate. The equation 14 is the final expression for material removal rate in case of ductile material. Now, so these for equation 14 and equation 11 are the material removal rate of brittle material as well as the ductile material respectively. So now we will talk about the some different model for material removal. So it was proposed by Pinde and San in their book that is called Modern Machining Process. It was published by Tata McGraw Hill in 1980s. Right. So according to them, they proposed one expression. It's like a material removal rate resulting from the chipping by assuming that from the chipping of the work surface by impacting abrasive particle. So they proposed one expression for material removal rate in case of AGM. So in this expression, capital Z is the number of abrasive particles impacting the surface per unit time. DA is the diameter, average diameter of abrasive grain, which is in micrometer in size. V is the velocity of the abrasive grain mixture. Rho is the density of abrasive material. HW is the hardness of the workpiece material, and this zeta is a proportionality constant. Removal rate also can be estimated using this model. So now I will talk about on third model, which is called erosion profile. So okay, so in previous models, we try to estimate the what will be the amount of material removal per unit time. Now, but what will be the shape we don't know. So here using this model, you can also estimate the cavity shape using some mathematical formulation. So it's like a how the final cavity will formed shape. So there are one cavity shape estimation was proposed by Bala Subramaniam, which was paper was published in Journal of Material Processing Technology. So this paper talks about erosion profile estimation, and they had some assumption like a erosion rate is proportional to the particle kinetic energy, similar to the our previous assumption like a kinetic energy will be a whole kinetic energy will be consumed to the remove the material. So same thing is like erosion rate is proportional to the particle kinetic energy. Then particles are spherical, no particle collision within the jet, like in between. Maximum mass moves at the jet center. It talks about the like a nozzle opening. So maximum mass of the abrasive mixture it will move at the center and minimum at the periphery. Linear velocity distribution along the jet radius. So this assumption you can see on the this below schematic diagram. So this is the whole, it's like a capital R jet radius, right? So it varies through the at center R is equal to 0 to at peripheral R is equal to capital R. So it's like a jet radius will vary from 0 to R, capital R. And then particle mass profile you can see just below, it's a, like a some parabolic profile is there. So this profile was mathematically expressed as here mr is equal to mx er rho sigma 1 square. And then particle velocity distribution, so it's you can see at the straight line from v naught to v1, right? And v naught will be the in the v naught v1. So here some terminology. Jet radius is denoted as a capital R, and radius at any point within the jet is R. Maximum particle mass in the jet is m max, with particle mass m naught corresponding to maximum number density q naught particle per unit volume, and the particle mass at radial position r is mr. So at let's say any point in the jet, so if the radius is r, then the particle mass will be the mr corresponding to the number density qr. So similarly, maximum velocity of incoming particle is v naught, and velocity at the radial position r is the vr, and velocity at jet periphery is v1, that is the v capital R. Based on that assumption, so they calculated number of particles striking on the target. It's like a qr, capital Q, it's a material removal rate into multiplied by velocity. So it will give you the number of particles per unit time, per unit area, per unit time. The mass of particle impinging in the targets. So if you multiply that equation with mr, so that will give you the total mass of the particles impinging on the target. So then erosion rate in AGM process can be expressed as P half into mass into velocity squared. So like again, P is a constant and multiplied by kinetic energy. That's the erosion rate. We assumed the erosion rate is directly proportional to the kinetic energy. That's why from there equation 16 comes. And if you will put the value of mass and velocity, then you will get the expression, final expression of erosion rate, as we can see in equation 17. Now if you will go to the detail, like each kind of value mr, qr, and vr, they had proposed this expression to estimate the profile of the mass variation, particle mass, then as well as the particle velocity variation, right? So as well as the particle number density profile, you can see here it's like a bell shape on right side. That is for the equation 19. So if you will put this value like a mr, qr, and vr in equation 17, then you can finally get the erosion rate, which is like a the equation 21 is the final expression. And this equation is used when to calculate the erosion rate. And when you will plot this, using this equation, make it normalized and plotted, then the actual cavity profile can be estimated of the erosion profile, we can say material removal zone. So that expression, that derivation was proposed by Balasubramaniam et al, right? So this is a good theoretical estimation to estimate the erosion profile. Now I will talk about process parameters in AGM. So if you will see here, the process characteristics of AGM can be assessed by four major characteristics, like a material removal rate, the cut geometry, surface roughness, or we can also say in a positive sense surface finish of the removal zone, and the rate of the nozzle wear. And these four characteristics will directly impact on the life as well as the material removal rate. These things will be directly, it can be influenced by the several parameters, machining parameters, like as well as the metal parameter, the abrasives, its composition, size, shape, and mass flow rate, then get the gas, the nozzle, etc. So I will talk about one by one and how these parameters will affect those characteristics. So here first thing is abrasive particles. If you will see, there are several types of abrasive materials. So aluminum oxide, and it is hard and sharp and durable, common use. Medium hardness material, metal, ceramics, advantage, produce fine finishes, effective on wide range. So similarly, silicon carbide, glass beads, garnet, and sodium bicarbonate. So each, in this table you can see for each abrasive types there are some characteristics and their common use as well as the advantage. So based on the application, abrasive materials get selected. So let's say for specific workpiece material, so for example, if you have soft metals to process, then you can use aluminum oxide and garnet. Fast material removal, you will get fast removal, material removal, and smooth surface finish. If you have hardened material like stainless steel and tool steel, then you can use silicon carbide for abrasives. Brittle ceramics for silicon carbide, advanced ceramic, aluminum oxide, right? For soft plastic, glass bead is also very effective. For example, polymer composites, aluminum oxide and garnet is effective, right? So this table helps you just to select the abrasive material for the to process the particular workpiece with particular material types. And now abrasive shape, size, and others. The exact shape of abrasive grain is not critically important, but they must have some sharp edges to ensure the effective wear. Let's say if it is perfectly spherical, then it will be material chipping action you will not get effectively right on the work surface. That's why sharp edges enable efficient macro cutting action. While the grains should have irregular shape to enhance their cutting ability, there should be minimal variation in their size. Right, so it's a very typical main thing. So like you cannot choose like a certain 10 gram abrasive of 15 micron, and then 20 abrasives for 100 micron. So this should be not very high variation in the particles. So that's why there are several filter sieve is used to separate the abrasive say particular size. Then abrasive is from 10 to 50 micron. Smaller size is used for finer finishes and precision. And reuse of abrasive is not recommended. There are several reasons, because once you will use first time abrasive mixture, so their cutting effect efficient, if you will use multiple times, then the cutting efficiency significantly decrease, because after the initial use. Because why? The contamination occurs, because once you will do the machining in AGM, so the removed particles, which is also forms in a some hot abrasives, right? So it will get mixed with the your abrasive mixture, and it will be very difficult to separate out, right? And this can, when they will again, then you reuse, then it can clog the nozzle's small orifice. So that's why reuse of abrasives are not recommended. Then mass flow rate. The mass flow rate of abrasive particle is influenced by the both the gas pressure as well as the flow rate. As the mass fraction of abrasive in the jet, like a mixing ratio, increases, let's say in a particular volume of the jet mix, if you will increase the mass fraction of abrasive, the material removal rate initially it will increase, as you can see in the schematic diagram on left side and bottom. However, beyond a certain point, further increase in the mixing ratio, means increasing the mass fraction of abrasive in the jet mixture, it will lead to a peak in material removal rate and then declining. So mixing ratio, it affects the affecting the cutting efficiency and surface finish. When the mass flow rate of abrasive increases, the material removal rate, and now if you will see the flow rate, it MR also increases due to the greater number of abrasive particle available on impacting on the work surface per unit time, right? So however, there will be some certain range of the mass flow rate which is best for the abrasive jet machining. So generally 2 to 20 gram per minute depending on the application. So now, if you will talk about the abrasive mass fraction impacting on the material removal. So initially, why it increases, as you can see in the diagram in the below on the left side, this one. So here, increasing abrasive mass fraction leads to the more particle impacting on the surface, resulting in higher frequency of impact, which eventually increase the material removal rate. Then at peak MRR, what will happen? Optimal maximum ratio will maximize the energy transfer to particles, yields the highest MRR. It doesn't mean that you are increasing mass fraction of abrasive in the mixture, it will increase material removal rate. No, this is not possible. It will decline eventually. So what will happen? So further increase in abrasive content reduces the gas particle velocity, because the same amount of gas must now carry more mass. Lower particle speed decreases kinetic energy and then cutting efficiency. Increased particle collision also dissipates energy and reduce effectiveness. It means there will be very lower amount of kinetic energy available on the work surface if you will increase beyond the optimal mixing ratio. Now I will talk about the gas. So velocity of abrasive mixture is like a gas mixture 100 to 300 meter per second, and higher velocity results in an increased material removal rate even when the abrasive mass flow rate remains constant. So if, you can see here from the diagram, like abrasive gas mixture velocity is very important parameter, and carrier gas pressure usually varies between 2 to 10 bar. Higher pressure increases jet velocity and material removal. Now to the come to the other parameter, that is nozzle. So criteria for the nozzle design: it must feature a pressurized constant feed system, achieve supersonic airflow, ensure uniform abrasive particle dispersion across its width, and withstand erosion for a long service life. So some of the materials used: tungsten, carbide, sapphire, and ceramics. Tool life depends on the which kind of material you have selected for nozzle. So let's say for example tungsten carbide, it working life is 20 to 30 hours, sapphire up to 300 hours. Nozzle diameter, it varies from 0.15 millimeter to 1.5 millimeter, typically 20 x larger than the abrasive grid size. That is the one criteria you can select the nozzle diameter. The nozzle orifice can be either circular or rectangular in shape, with a cross-sectional area ranging from 0.05 millimeter square to 0.2 millimeter square. Then another very critical parameter, we call it nozzle tip distance. Sometimes we call it standoff distance. That is the distance between the mm, or we can say gap between the tool and the workpiece surface, and it is usually varies between 0.25 millimeter to 15 millimeter. Shorter distance lead to deeper cut and higher material removal rate up to a optimal point. And if it is a larger distance, then it will be the less deeper, but curve width may increase. And the also impingement angle, like from where, at which angle the abrasive particle impinges on the impact on the workpiece surface, it should be lie between 60 to 90 degree, with 70 to 80 degree typically offering the highest material removal rate. So here you can see the effect of nozzle tip distance. If you will see here, if you are increasing nozzle tip distance, gap between the tool and work surface, so the crater width that we call w1, it increases as well as the, but depth is decreasing continuously, right? So larger standoff distance results in a wider curve, or we can say cut width, and reduced depth and precision, which you can see on the schematic diagram. So if you will talk about the impact on the material removal rate here, so there's a one plot. So I can see here, as standoff distance increases, the material removal rate initially increases to an optimal point and then decreases. Larger study results in a wider curve, as we saw in previous schematic. And the optimal SOD depends on the several factors. It will also include nozzle diameter, abrasive size, pressure, workpiece. So it is not like a single parameter influence, right? So at the same time, multiple parameter will influence the overall material removal rate, surface quality, surface finish, surface roughness, right? So you can see the in the summary, SOD range, it is short. The effect on machining, it will be high MRR, deep cut, narrow curve. Remarks, it's a high energy particles, nozzle wear risk, and low MRR and wide cut. So now overall summary of abrasive jet machining. So up to this mark, we discussed about the basic principle, the component of the abrasive jet machining system, then material removal rate estimation, then erosion to cavity shape profile estimation. Then we talked about the process parameter influence, and then, so if you will compare with the other machining process, so let's say if you will compare it with sandblasting, so while both processes use abrasives, abrasive as AGM operates with much higher precision and is used for finer material removal. If you will compare with the water jet cutting, so it's similar to the abrasive jet machining, except that instead of gas, water is get mixed with the abrasives. So it's like a wet process we call. And AGM versus laser cutting, so laser cutting is more efficient for material than that can absorb laser light, while AGM is better for the brittle and hard material. Laser machining process is also expensive than AGM, because laser generating machine is very expensive. So conclusion, AGM is an excellent choice for the precision machining of brittle, hard material like glass, ceramic and composites. It offers the advantage of no tool wear, minimum thermal effect and high precision. While it has limitation in material removal rate, in operational cost, it remains a valuable process in industry till now, requiring fine machining and etching process. So now you can see the some worked out example based on those theoretical estimation. Right. So let's say this example one, if let's say abrasive jet machining process, the mass ratio is 0.8 and the ratio of density between the abrasives and the carrier gas is 20, then how you can calculate mixing ratio? So using this expression, you can estimate the mixing ratio. So similarly, in example 2, the diameter of the nozzle is 1 millimeter and the jet velocity is 200 meter per second. Then what will the material removal rate? So once you will calculate cross-sectional area of the nozzle, then you can estimate the volumetric flow rate. So these are the some reference material like I followed to make this PPT. So there are several books like from Professor VK Jain, who taught me, especially in when I was doing I was graduating in IIT Kanpur. Then Amitabh Ghosh and Malik, but Vijay Bhattacharya from the Jadhav University, Yusuf and Bala Subramaniam and et al., which is very good for the if you want to read more in detail. So If you have any question or query, you are welcome to suggest, or you can also ask questions on the comment section. Subscribe to my YouTube channels, Nirbhik Sen Yogi and Nirbhik Gyan. Kindly note that Nirbhik Gyan is especially for the academia, so eventually I will move into that channel for this kind of stuffs. So now in the next lecture I will talk about ultrasonic machining very soon. So thank you very much.